Okay, so it's our great pleasure for the first talk of this semester to have César Galindo from Universidad de los Andes, Bogotá, Colombia. And he will talk about braided zesting of Verlinde modular categories and their modular data. César, please.
Thank you very much, Sebastian. And thank you for the invitation. It's a great pleasure to be here. Okay, well, I want to talk about something in what we have been working with Eric Rowell, really Julia Plagnik, Colleen Denale, Shin, and some students, in particular Giovanni Mora, that is trying to produce new examples of particular modular categories. So the idea behind of this construction is, let's say, a innocent way to modify a little bit part of the information of the modular category in order to produce a new one. So it's, let's say, just a mechanism to produce new modular categories. Okay, so let me start more or less from the beginning. And if you have a fusion category, that I don't want to remember the whole definition, because in many sense I don't need at this moment the full definition. We have associated with the fusion category some combinatorial object that give us a lot of information, not all the information, but give us a lot of information of the fusion category that is called the fusion ring, or really the Grothendieck ring, that if we axiomatize the basic properties of the Grothendieck ring, what we obtain is the notion of fusion ring. And what happened? Yes. So what is this, let's say, this combinatorial information? This combinatorial information came first from, if you consider the set of all isomorphism classes of simple objects, I will denote this set at this moment as a I. And then we have some integers that in this case corresponds to the multiplicity. I mean, if you take two objects in the category and you do the tensor product, the object C perhaps appears in the tensor product with some multiplicity. This can be computed as this dimension, but the important part is that this is a non-negative integer. So the fusion rules are just that. It's this set of elements with this set of numbers associated with these three labels. And in addition, but this is in some sense, let's say, this is some property. We need an evolution that is given by the fact that in these fusion categories we have duals, and dual of simple objects will be again simple. But what exactly a fusion ring is? Well, it is a finite set with a distinguished object that sometimes people call 1, sometimes people call 0. It depends, and probably I will confuse at some moment. I will mix the notation, I hope no. A set of non-negative integers. And the idea is that if you consider the free abelian group with the basis given by this finite set, then you can define a product using as a constant structure these numbers. And the idea is that you obtain an associative algebra with the unit object, the unit element given by this one. So of course, they will impose some conditions over these integers that are just rewrite what exactly means associativity and what exactly means that this is the unit in terms of these non-negative integers that sometimes, yeah. Okay, and the other ingredient in this case is the involution, that as the basic things that we need is that it defines for this product an algebra anti-isomorphism, and there is some compatibility between the unit. And here the idea is that there is this compatibility that this number has to be in general just 0 if B is different to A dual, or yeah, and 1 in other case. That's the additional information, and we can prove that if an involution of this kind exists, in fact, this is unique, and it has a lot of additional consequence on the fusion rings. What are some examples of fusion rings or fusion rules? Well, I think the basic one that perhaps most of us has in our mind is the set of irreducible characters. Suppose that you have a finite groups and you consider, let's say, finite dimensional complex representations. Then you have associated characters, and in particular, you have associated irreducible characters. And we know that when we multiply two of them, they express as a linear combination. And this linear combination, in fact, is exactly the multiplicity again of the representation associated with the character labeled by K inside of the tensor product of this. And the involution is given just by the dual, or in this particular case, just by complex conjugation if we are working on the complex number. This is a typical example. And another one, it's supposed that the finite set is just of labels of simple objects. It's just an arbitrary finite group. Then using the group, you define a product, and the product is just the product of the group, and the evolution is just the inverse of the group. Let's say that those are two extreme examples, but in many cases, we are really interested in examples that are very far from these two. However, in order to have some intuition about fusion rules, I believe that those are quite important. In particular, if you, there are many properties of the representation of groups, or many notions, let's say, that can be rewritten only in terms of the fusion rules. And this is and this example, of course, is the key example in order to understand notions like nilpotency and other ones. Let's say dimension, other kind of examples. But this, as I said, this part of the information that is quite interesting, let's say the fusion rules are not enough in order to have the whole, or to capture the whole structure of the fusion category. I haven't defined what is fusion category, but at least at this moment we know that a fusion category has this combinatorial object behind. But again, that's only part of the information. The other part of the information, basically, it's given by something that some people call 6J symbols of F matrices. And the idea is the following: you fix a vector space of dimension given by the integer. So we are assuming that we pick fusion rules. And then the idea is that you fix a basis, and sometimes there is the diagrammatical notation for the basic elements. So it's just a basis that depends, it's a vector space with 3 labels, and there is one extra label that is given, by the dimension. Suppose that this has dimension 4, so there are 4 mu's, different mu's in this particular case if the dimension is 4. And the idea is that we need, in addition, an isomorphism between this vector space that corresponds really to the composition of an object between 3, well, doesn't matter at this point, but there is some isomorphism between these two spaces, and again, there is a diagrammatical notation that is used, I mean, to label the natural basis induced. I mean, if you have this basis on this vector space, so this also has a natural basis given by the tensor product of the bases, and this basis there is denoted diagrammatically in this way. And so we have an isomorphism that assign, this is the idea, to I mean, it's an isomorphism from here to here. So in particular, to this basic element, it's associated a linear combination of the bases in this case. And then we have a lot of labels. And in particular, we have 6 labels. And this is the reason why it's called 6J symbols. But the point is that this isomorphism, because at this moment I haven't said anything in particular, because I haven't imposed any condition on this on those matrices or linear isomorphisms. But the idea is that they have to satisfy this equation that is, again, is a diagrammatically, I mean, but that has a concrete equation that is given by this. This is a nonlinear equation. It's very complicated in general to solve. I mean, the idea is that if you fix a fusion rule, then you have you have these equations, and this is a solution of this equation really give you the whole information that you need in order to recover the fusion category, basically. I mean, this is the really hard part in many cases. Yeah, so again, the point here is that in general, if you have fixed fusion rules, it could be very complicated to have a concrete solution of this. So, for example, what is the idea behind of this notion that we call zesting? Again, the plan is to give a method to construct new fusion categories. But before really think about new fusion categories, perhaps a more innocent question is how to construct new fusion rings. So the idea is to use something that is very well known in group theory, that is just to change a little bit the multiplication using a Tuco cycle. But here by a Tuco cycle, we have to be careful what we really mean. So the idea is that you fix now a group, let's say a finite group G, and then we can define the notion of a grading. So a grading, it's a way to assign to any simple object, to any element in this basis of the Grothendieck ring or of the fusion rings, an element in a group, in such a way that this assignment it's compatible with the fusion rules, in the sense that if you fuse, or if you do the tensor product of 2 simple objects, and this object A is graded, have a grading, this grading, and this simple object B has this grading, then if an object C appears in the decomposition, it should have, the grading should be the product of these two. Yeah, so express again is exactly this equation. And now the idea is, okay, if we consider only those simple objects that are graded over the trivial, over the unit of the group G, in fact, this is a fusion subring. Okay, so it's a subset that is closed by tensor product and also is closed by the involution. So this is a subset. And the idea now is that in this part, we can consider elements that are invertible. Invertible means here that, well, really central. So here we need central elements in the Grothendieck ring, but additionally that, I mean, in the simple object that has degree 1. So the assignment to the group is exactly the identity, and also that the involution, the product of the element A with the involution, it's equal exactly to the unit again. So this is in fact a group, an abelian group. So now if we have an abelian group, we can proceed very similar as the typical idea in group theory, and we can consider a two-cocycle. What is a two-cocycle? It's just an assignment that to two elements in the group, we associate an element in this abelian group. Okay, and then this two-cocycle, and in principle, if you can, you can take any function. So you can in principle take any function that given a pair of elements of the group, assign an invertible object, an invertible element in this abelian group, and then you can define this new product. Okay, so it's just the old product, and you twist a little bit by this invertible element, and now you can ask what are the conditions in order that this product again is associative. This is a very old condition, and it's the condition that is called a two-cocycle condition, for example, in group cohomology. And then it's a simple exercise to see that in fact, you get a new fusion ring with the involution given by this formula. Okay, so again, only using this very simple and in general very easy to compute trick, we can produce new fusion rings. So of course, here appear some natural questions. As I said, given a fusion ring, in general, to know if that fusion ring comes from a fusion category, it's equivalent basically to find an explicit solution of this equation. Or in other, yeah. And this kind of fusion rings, they are called categorificable, that admits a categorification, perhaps better. So the natural question is, suppose that we have a fusion ring that came from a fusion category, then we apply this modification by a two-cocycle. And let me say that this two-cocycle really can change a lot the fusion ring. In the sense that, not terribly, but it changed. For example, you can go from something that is self-dual, that every element is self-dual, to something that is not. So really, you can change a lot the category. But the point is, suppose that this R came from a fusion category, then the natural question is when R lambda also came from a fusion category.
Can I ask a question, please?
Yes.
Just the previous slide. Is there room for non-trivial zesting if there is no grading? Like the grading, only a trivial grading?
Oh no! If the grading is trivial, I cannot apply the trick. Because this will be trivial, so there is only one possible assignment, that is the unit object, and in this case, then we obtain exactly the same multiplication. So we really need, in order to apply this construction, to have a non-trivial group, a non-trivial grading that is controlled by some universal grading group that Dmitry Nikšić and Jelaki, Sholon Jelaki defined many years ago. But yes, for this construction, really, the non-trivial grading plays an important role.
Thank you.
Okay, so In this paper, we study exactly this problem. And we give a complete solution, let's say, that in many sense, of course, is based, not explicitly, but implicitly, on a previous work of Pavel Lettingov, Dmitry Nikšić, and Viktor Ostrich. However, our approach is very, let's say, computational. I mean, we can really produce formulas, let's say, for the concrete formulas for the abstraction, cohomological abstraction, that tell us when this kind of categorification exists and when it doesn't, and also formulas for things like modular data and other things. Let's say that this is perhaps the biggest advantage of this notion. But again, this is a particular notion of a more general theory of grading fusion categories. But at this moment, if you see, I haven't, I mean, in the title of the talk, I said something about braided fusion categories. And I haven't said what a braided is in this context. And the braiding will play an important role, because what at the end I really want is to deform, and this is not contained in this paper of Pavel, of Ettingov, Nikšić, and Ostrich. So what we want is not only to get a new, let's say, we would like to start with a braided fusion category, change the fusion rules to obtain a new pentagon solution and another, let's say, solution to the pentagon equation, but also to get a new braiding and to understand when this kind of procedure is possible and when it is not. So first I need to say that, at least in this general terms of fusion rules and F matrices or 6J symbol, what a braiding is. So one condition that we need in order to have a braiding is that the fusion rule should be commutative. So that in particular translate that this couple of numbers should be equal, that in the category corresponds to, really here is not equal, it's to have an isomorphism between these two objects. And then in addition, we need to fix something that physicists call R symbol, that corresponds just really an isomorphism between this vector space and this vector space, that sometimes it's again that diagrammatically written in this way. And there is an additional condition that came from this idea of braiding, that again diagrammatically is written in this way, and they correspond exactly with the hexagon axioms of braided tensor categories, just written in this language. That again, it translates to a concrete equation that I want to write. So there are two equations are bigger than the pentagon equation, and I think that this moment it doesn't really clear what is happening. But something that again, in general, it's interesting is that these kind of equations, even that sometimes looks more difficult, in general could be easier to solve than the pentagon equation. Or to say something, sometimes it's easier, sometimes not, but in general, let's say the more complicated things could be to find a solution of the pentagon equation still. So what is the plan of the remaining part of the talk? I am not finishing yet. It's just that I don't want to remember the whole theory of braided zesting, of the whole results, because I want to, I mean, this is some result that we did like, I don't know, 3 years ago. And I would like to talk about like a new, different approach, not completely different, but that we did with Giovanni Mora and Eric Rowell. Giovanni, it's an student of Eric and mine, that we are the advisor of him. And the goal of the paper and the things that I want to present, it's two things. First, if you have this kind of rated fusion categories with an additional thing that is called a spherical structure, you have some combinatorial data again. I mean, in general, again, the fusion category and the braided categories and all these things are complicated objects. However, they have some combinatorial things that in general could be easier to understand and easier to compute. And one of the things is that we prove that in fact, the whole information that you need in order to apply Zesting and to compute Zesting, it's already contained in this combinatorial gadget that is called modular data, that I will remember in a second what it is. And also apply the ideas, because for Verlinde modular categories, they are some kind of categories that are constructed as a semi-simplification of the tilting modules of some quantum groups in some special values of the root of the unit. There are already a very good understanding of the modular data, this kind of thing. There is a combinatorial description of the modular data in terms of the root system associated with the simple Lie algebra. So the natural question is, I mean, and something that also is quite interesting is that in general, we don't have a complete description of the fusion category, in the sense that, I mean, if we pick an arbitrary Verlinde category, we don't know exactly how the F matrices are or how exactly the R matrices are. So we really don't know exactly, for many cases, the fusion category itself. But something that we know, it's the modular data. So in particular, we can apply this construction with the knowledge, the current knowledge of the Verlinde category, and that was the idea of the paper. Okay, so in the same way that I introduced the fusion rules as some combinatorial gadget associated with fusion categories, here we also can associate some combinatorial data to an spherical braided fusion category. So the idea is that there is, when you have a braided category with some additional condition that is called to be spherical or to have a ribbon. This is, I mean, they are equivalent. To have a ribbon is the same as to have an spherical structure in the case of braided fusion categories. But the point is that if you have this additional structure, given any morphism here, this is a typical notation that is used, and this represent a morphism in the category that goes from taking tensor product of A1 to AN. Here there is some map to A1 to AN. So this is just a morphism. And the point is that you can associate to any morphism here. Sorry, it should be, in this particular case, it is kind of a confusion without the primes. It's a map from here to here. You can associate an scalar that in many cases has a very nice interpretation in terms of ribbon invariance or invariance of ribbon knots. But the point is that you can construct a matrix, a complex matrix, index on the simple object or on the braided fusion category, one associated with the invariant associated with the Hopf link, also, there is a special scalar that is called the dimension or the quantum dimension that is just associated in this particular case with the circle index by A. So really it corresponds to the trace of the identity. And here really it corresponds to the trace of the double braiding of one object with the dual. And in addition, we need, here, this procedure gives us a matrix that is called the S matrix. And if we apply the trace to the braid and then we divide by the dimension, we obtain a number that is called the ribbon, or one scalar that is associated to the ribbon. And then we can produce a diagonal matrix that is just to put these numbers in the diagonal, and this is called the T matrix. So for every braided spherical category, we have this S and this T matrix, and this S and this T matrix is called the modular data. If this matrix is invertible, the category is called modular. So a modular category, it's a spherical braided fusion category with this matrix invertible. There is many ways to rephrase the modularity, some of them very useful, but for the talk, I think it's not necessary to remember anything of these equivalent conditions of modularity. Okay. Some people have tried to, let's say, to axiomatize what an arbitrary modular datum is. Really, to be honest, here we are not absolutely interested in to know what is the best axiomatization. Let's say that the best axiomatization, at least for me, is that it's an S and a T that came from a fusion, from a modular category. But in any case, there are basic properties of this S and T that allow us to prove many interesting results and properties of the fusion category. So again, a modular datum over a finite set with a distinguished element 0, in this case I did a change, is first a complex matrix and a diagonal matrix such that the matrix S is symmetric. These elements that are defined, in this particular case, they will correspond to the quantum dimension, are different to 0. This scalar in this 0 element will be 1. And this is perhaps the most important condition, that it's the Verlinde formula condition. And it's that if you have, we can define, let's say, a function over the, this notation is the set of functions from I to the complex numbers. We can define a function for I to the complex number by this equation. So it's just xi evaluated in j is the value of the si j over this quantum dimension. In the case of braided fusion categories, they correspond to do this particular diagram, if you know. And the idea is that these functions will define inside, this has to form a basis. This is a condition. And it has to be a fusion ring. Yes. This is again to say basically the Verlinde formula. So the point is that associated with a modular data, explicitly we have a particular fusion ring. The fusion ring is the fusion ring generated inside of this algebra, this commutative algebra, by this particular basis. Yes. And this is some additional conditions. The dimension has to be invariant under the involution. The same with the T. and the value of the t on the trivial element, again, should be 1. And finally, the S and the T should define a projective representation of the modular group. And this is the reason why these kind of categories are called modular categories. There is, of course, an explanation of why exactly this happened. But again, I think I don't have enough time to explain or to say something about that. Yes. So, yes. So let's say that this is the kind of axiomatization of modular data that will be enough for anything that I need. And to be honest, really, this condition is not absolutely necessary for most of the things that I will do. Let me introduce these Verlinde modular categories, and really what I more care about is the modular data associated. So the idea is you start with a complex, simple Lie algebra, and you fix, let's say, the associated irreducible, in this case, root system. We need to fix an integer that should be bigger than the Coxetel dual number. I will explain in a second what it is. The Coxeter number is defined through this kind of formula when this row it's half of the sum of the positive roots, and this theta it's the highest root, and this number is defined as this particular equation. Here I put in this table some values just to remember. For example, for the case of SLN, the value is n plus 1. Yeah. Really, in the case of SLN, the associated, let's say SLN plus 1 that has a root system associated AN, the Coxeter numbers is n plus 1, and the same numbers for the other. And so in addition, we have an integer, as I said, and a root, some root of the unit. In a table that I will present in a moment, I will say exactly what root of the units are this cube. But the point is that you have some root of the unit. Give me a second, and then the set of labels are all weights, let's say positive weights, that satisfies this equation. In a second, again, I will try to give an example. And the S matrix is computed, again, using this concrete formula that is given in terms of the product of the root system, this row that I explained here, and some sum over the Weil group of the root system. And again, the T matrix, it's described using this product. The point again is that this is I mean, in general, of course, again, could be kind of complicated depending on the size of the group explicitly compute, that's by sure. But this is a very nice and concrete formula that can be applied in order to first to compute the modular data, but then applying the Verlinde formula to compute the fusion ring associated, to compute the quantum dimensions, and to compute more things. Yes, as to explain again what the Q are, it depends, as I said, in several parameters. One is this dual Coxeter number, and there are also some number that will depend of, I mean, like these two here appears to 2, but yeah, it will depend of the kind of yeah, it will depend of the root system, and if there exists a long root or a short root, and the quotient of those. For example, in the case of S, oh, I haven't introduced the note. Yeah. There is a notation that sometimes is used a lot in physics, physics papers, and it's that for AN they use SUN plus 1. That is, I mean, if we know compact groups associated, this is quite natural. And the same for the other. So SO, SP, SO, and the same for the other. So the example that I want to present is this one. Consider the case of A2. So the root system has, it's of rank 2. And in this particular case, if we draw the root system, the condition that I said that should satisfy the elements in the vial chamber will correspond to some particular integer combinations of the dominant weights. Yeah, that has a nice picture. And in particular, again, for the case of SU2 level K, this is one of the very few when we can have a closed formulas for the S matrix, the T matrix, and of course, well, for the fusion rules, it's possible to have for even more, but in general, these kind of formulas could be complicated in general to have, let's say, closed formulas. Of course, here, the vial group is very simple. It's the cyclic group of order 2, so these computations, again, are quite simple, so that's why we can have very nice and compact formulas for the S and the T matrix, and also for the other. In general, this is one first things that we need to do if we want to do explicit computations. We can, I mean, if we take any weight positive here, we can express as a linear combination of the fundamental weight. And in general, in this particular case, we need to only to consider non-negative combination of the fundamental weights. And the idea is that you can express, in fact, or you can index, perhaps it's a better word, the simple objects of these categories just as an n tuples of integers, non-negative integers that satisfy some very simple condition. For example, in the case of SUN, this is the condition. It's just that the sum of all components should be less than equal to K. And there are other conditions that appears once it's just a basic computation. But it's very useful later in order to have concrete formulas. Okay, one of the things that we need in order to apply this zesting for modular data, it's the notion of the center of a modular data. So if you have, remember that I said that if we have a modular data, we have associated a Grothendieck ring. So if we have a Grothendieck ring, in particular, we have the set of all invertible elements that are those that when you multiply by the dual, you obtain the vacuum, the trivial object, the unit object. Yes, so when these refer to the product in the fusion ring associated that perhaps that remember is I mean, formally in this case, is just the algebra of functions from I to the complex number that has this particular basis that are described in terms of the S matrix. Only the terms of the S matrix. And the point, and this is the nice things for the construction, is that the fusion ring is really universally graded in the sense that any other possible graded came basically by a quotient over the, I mean, remember, sorry, I did a mistake in the sense that instead of called CM, it should be A. Here by this A, I'm referring to the center of the modular data. So this A corresponds exactly to this group, these all functions that satisfy this condition. And the point is that the group is, I mean, this is a finite abelian group. So the point is that this is universally graded over the dual of the center of the modular data. And the grading is very simple. Remember that this xi corresponds to a function. So the grading is just given by taking the function and evaluating in the elements of A, and this will gives you a character of this group. So it's very natural, the grading. And in particular, remember that because we have a grading, then we can take those elements in this group that has trivial grading. And this is something that happened for very general theory of modular categories, but this, the T matrix, for the T matrix, always exists a bicharacter that takes values only in 1 and -1 that satisfy that for this part, the T comes from the trace or from C of AA. I mean, this is something that in general happens if the modular category, the modular datum came from a modular category. So this is a condition that all we will have, because these, I mean, the fusions of category associated with this part always should be something that is called symmetric. So this bicharacter always should exist. So in the case of Verlinde categories, the center has a very nice description and a very nice interpretation in terms of the center of the simple connected Lie group associated. But for example, in the case of AN that has SUN plus 1 associated, if you remember, the center is given by, the center is given by this group. And again, for these three, the center corresponds to C2. And in case of DN, there is two variations. One is when N is odd. In this case, it's a cyclic group of order 4. And if N is even, it's the claim 4 group. In E6 is this group of order, cyclic group of order 3. And those doesn't have the same for the other, for F, and and those doesn't have they have trivial center. So Sebastian asked about what happened if the grading is trivial. If the grading is trivial, we cannot apply this construction. And the grading in this part, it's dual for Verlinde categories, it's dual to the center. So for those categories that have trivial center, we cannot apply our construction. So we are only interested really in the case of A6, DN, E7, CN, BN, and AN. For the others, Zesting won't apply anything. And the other nice thing that it's quite useful for us is this result of Sawin that tell us exactly what fundamental way corresponds to these invertible elements. And so we can even to say the explicit what is a generator of AN, what is a generator in these cases, and what are generators in each one. So using and fixing generators for each case, we can explicitly describe the grading, because as I said, there is a grading associated in the case of AN over this group, in those cases over C2, and these cases over this, and we can to produce explicit formulas for the grading in terms of this description that I said before. And the same for this, if you see, most of the cases except for this one, DN for N even, all of them are cyclic. This is the most strange case, let's say. So I put here the case of cyclic grading, and here is the non-cyclic grading. Also, we have formulas for this particular case. And again, this will play an important role. That's why I am talking about that. And now what is Zesting finally? Yes, because I have said many things, but I haven't. In this particular setting, a Zesting is something quite simple. It's just, you need to have a 2 cocycle, an ordinary 2 cocycle, because this is an abelian group, and this is again an abelian group, so you can consider it just an ordinary 2 cocycle. You need a 3 cochain, and by a 3 cochain, I just mean a function that takes 3 values of this abelian group and assign a complex number, and also a 2 cochain, so it's a function that two elements of this group associated a complex number here, and it has to have satisfied three equations that in principle looks kind of ugly, but they have a cohomological interpretation. This is just that the differential of this omega is equal to the cup product of these two. And here, this is explicitly what I mean by cup product. And if you remember, I said that in this trivial part, I mean, in this part, we fix bicharacter. So this bicharacter is used in order to produce the cup product. And later we have associated another condition that we call H2, and this is another condition. Just to say, the idea is that this condition will imply the pentagon equation, this condition will imply one hexagon equation, and this condition will imply the other hexagon equation. Basically, we are trying to rewrite many of the things that we did in previous paper, just, let's say, in order to do very explicit computations. So now, one natural question is, now, suppose that you start just with this data and you want to know if this data can be, I mean, if you have suppose that you have a two cocycle with this bicharacter, and then you want to know if there is some omega that satisfies this equation, and also an L that satisfies, sorry, here there's a mistake. Instead of L, it should be T. And if there exists a T that satisfies at the same time these two equations. This is the typical question. And the point is that this element, we prove that it's, I mean, we don't have to prove, it's something very well known. This element is a four cocycle, and in fact, the equation H1, it says this equation, it's only saying that the cohomology class of this, it's trivial. So the first obstruction is very simple. It's just this cohomology class, it's 0, and this is something that in general, because we are working on abelian group, is quite easy to compute. I mean, not trivially easy, but with some help of the computer, or let's say for cyclic group, we already know by heart that always is 0. For another example, like the claim for group, there is some work to do, but it's not really too complicated. And now suppose that we have a solution of this thing, then we would like to know if there is a solution of this H2. And again, there is a way just to doing some product over some kind of permutation and to checking if this function that you obtain is the function 1, if this satisfied for every 3 elements there, and then it's we can prove that in fact there is a solution to the H2 equation, and then we even can prove that this formator over the set of elements in the H upper 3 that satisfies this additional condition. So again, that gives us a procedure to follow. And then if you have something that satisfies the equation H1 and H2, then we would like to know if there is something that satisfies H3, and this is again just to check that some cohomology, in this case on H upper 2 with coefficients in this other group, are equal. So again, because we are interested in many cases in cyclic group or the claim for group, let's say at least for the case of Verlinde category, most of these computations are kind of easy to do by hand even. I mean, we don't use too much we didn't use the computer we used just to verify at the beginning if something happened or not, but later everything was done analytically. So what are the results in the last minutes? So the results are that we can produce, let's say to give some conditions on the level of the molar category of the Verlinde category in order to be sure that there exists braided zesting. This is kind of technical. I don't want to enter in details, but there are some conditions. If these conditions is not satisfied, then we know by sure that we can not do anything in order to produce an interesting example of braided zesting. And then we have a table that, again, I don't want to read case by case because it's too far, but it's a very explicit table that parameterizes the braided zesting in each case. I mean, that tells you even formulas, closed formulas how to do it, and we even implement most of this formula, at least in the case of SUN plus 1. And so we have explicitly what are those. And then this is, for us, our goal. We have closed formulas again for the new modular data. So you start with a modular data that came from one Verlinde category. You pick one of these Zesting parameterized by all these elements, and then you want to have a concrete formula for the new Zesting. And the idea is that for the new modular data. And the idea is that they will change just by some scalars that appear in these powers. The gamma, it's a particular value, and we have four closed formulas again for the power and for this beta x. So if we already know what the t and the s is, it's very simple to even implement in the computer and to say what are the new modular data. So in particular, what are the new fusion rules? And the good thing is that we know that those fusion rules really came from a modular category. So we are producing new modular categories. Just as examples, I mean, in the paper, there are several examples, but here I am only presenting one, and it corresponds to SO7 level 2. That is, if I remember correctly, corresponds to B. This is a set to grading. I mean, those are the fusion rules. And the important part here, just to say, is that every object is self-dual. This is something that we can see from here. I mean, the tensor product of 1 with 1 appears the 0 here and the same. But when you do the Zesting, these objects in red are not already self-dual. So the fusion rules really change a lot. And again, it's kind of technical, but in the case, I mean, here I present only the cases for cyclic groups. And there are, I mean, the case of SO2N is the most technical. It took a lot of time to have the formulas. It's particular because many abstractions were implicitly non-trivial. But again, we have concrete formulas for any S and any T in all cases, and even we present some examples like SO12 level 2, where there is some grading again over the claim for group. And the nice thing again is that this fusion category is self-dual, and depending on which co-cycle do you take in order to do the Zesting, you obtain things that are non-self-dual. I mean, the self-duality in particular is something very simple to check if the modular category change or not. Okay, that's it. All that I wanted to say. Thank you very much for the attention.
Thank you. Okay, so now we can ask a question. So, should I put the mic? Do you have a question?
Yeah, I'm here.
I can put the mic on.
So to do braided Zesting, you need the Mueller center of this pointed part, right?
Right. That's important. Yeah.
Why? So if you so this guarantees what you get after Zesting is braided, right? Or so my question is this degeneracy of the degeneracy really needed in Zesting if you only want associative Zesting, not braided?
Yeah. Yes. Okay. I didn't say explicitly, but what I was using in the case of modular categories was directly the universal grading. And there is a result that tells that the invertible elements in the trivial component lives really inside of one symmetric part. So if I want to use the universal grading, this is, I mean, in order to produce new braided categories, this is a necessary condition. However, If I mean the general construction that we did in one of the first papers, it doesn't need that the grading it's the universal grading, and in that cases this condition can be relaxed. And also the construction of the construction is not only for braided fusion categories. In fact, this is the condition works very well for fusion categories that doesn't admit any braiding. The point is that it's more technical to explain because we need to enter with centralizers and other parts that I didn't want to do
It's
in the talk.
interesting. Maybe did you try to do it even on Tamara Yamagami with the odd group?
Yes, well,
That's
there is a point there. I mean, this is a good question, but in the Tambara Yamagami with odd, the point is that the second cohomology group will be trivial because the grading always be order 2 and the invertible element will be odd order, so the cohomology vanish, so we cannot do many interesting things. But I agree. I mean, for example, if the Tambara Yamagami it's even the other part, then we can apply this construction. Of course, cannot be, let's say, kind of modular in the sense that yeah. But in any case, it's interesting.
Right.
Thank you.
And also, it's the quantum dimension. So in the Verlinde case that you studied, after
Yes.
Zesting, it seems when the fundamental group is cyclic, is the dimension fixed? I think S is different by a root of unity, then the dimension should be fixed.
Yeah, when you said the dimension, you refers to the quantum dimension of the
Yeah.
simple object?
Yes.
Well, yes, this is something that in general happened. I mean, in general, even in any case, the Perron-Frobenius dimension doesn't change because it's some kind of computation that is kind of easy to see that the same function define a ring homomorphism to this new twisted, let's say, fusion ring to the real positive real numbers. So in particular, because in some sense, I mean, yes, because the change in the multiplication is, I don't know how to say it, but the point is that the quantum dimension of the object doesn't change, and also in particular the global dimension doesn't change for any testing.
So in particular, if I consider the 16-fold way of PSU2 level 4K plus 2.
Yeah. This is an excellent question. I mean, in the case of 16-fold way, applying Zesting, we only can get 8.
Oh.
8. I mean, there are a lot of examples, as you probably know, of 16-fold way when the rank of the category change even.
Right.
The number of simple objects change. And here, this construction doesn't change in particular the number of simple objects.
That's what seems to be a little confusing. Okay,
Yes. So we only can get half of the 16-fold ways using Zesting. The other half is not possible to achieve with this construction.
Okay. Thank you.
Yeah. Thank you.
So I have a couple of questions which will be more basic, in fact. So at the beginning of your talk, you mentioned a zesting for the fusion ring. And maybe I missed something, but did you say, is it always category, if you have a Grothendieck ring and you have a zesting, is it always categorifiable or not? The condition of zesting for the ring you mentioned, for the fusion ring. If I want to identify
this part,
if admit a categorization does, yeah, okay, yeah. So this is not always it's a question, or is it? It's not an open problem. It can.
No,
apply-
it's not an open problem. In fact, the solution is that we can associate with a Zesting a Fourier cycle.
Yeah.
And the categorific, the conditions to admit again a categorification is just that this abstraction vanishes.
I see. So this is what you said for braided. You have the Pentagon equation equivalence.
Yes, but also it's true. Yes, but also but also it's true for the F matrix. Yes.
Okay. So it's
Yes.
okay.
In general, depending of the group, could be a kind of hard computation, but it's a very concrete computation. And it's
Okay. The next question is, yeah. So as we discussed, if there is no grading, there is no zesting. In particular, if the fusion ring is or the fusion category is simple, is non-trivial simple, it cannot have zesting.
Absolutely. Yes. There is no way in this case to.
So you mentioned so plenty of example Verlinde type. So this example are not, the example you mentioned are not simple, but there are some simple subcategory or simple quotient. I don't know which one. You can there are well-known quotient or subcategory which are simple. When you consider the Verlinde category, the usual simple category of the type, there are subcategories. Yeah. So is the zesting of this non-simple Verlinde category has a simple subcategory which is different from the beginning. You have a Verlinde category, it has a simple subcategory. Now you apply the zesting for the Verlinde category, and if you consider the subcategory, can you produce new simple category like that, or it will be the variant on the simple subcategory?
The point is that if the category is non-graded, I cannot apply the construction. And if already has a grading, it cannot be simple because the trivial component already is a fusion subcategory. I don't know if I am understanding correctly the question.
I think what he's asking is you can do the testing for the big category, right?
Yeah.
After that, you get a new big modular category that is not simple. But the original category has a subcategory that is simple. Then after zesting, right, the new big category should also have does it also have a simple subcategory? That is, yeah.
I see.
Is it new or not?
And is it different from the previous?
Oh, I see what you mean. I don't know really I don't know. I haven't studied. The fusions of categories of some families are kind of known, but in general, I think there is no classification. This is a good question. I have no idea what kind of thing can happen with, yeah. Okay, yeah, I understand. It's like you have a simple fusion ring that is embedded in something bigger that admit this zesting. Then you apply the zesting, and probably this thing in the middle also can change. I really don't know, to be honest. Yeah, probably. In principle, it's possible because there are more information outside that yes. But to be honest, I haven't paid attention to the question. Yeah, thank you.
It will be nice if something new can happen like that.
Yes,
for simple. Okay, interesting. Then yeah. So now if you don't mind, I have some more general question. In fact, I am looking for simple integral modular fusion category, and in the family coming from Lie theory from Verlinde, there is nothing is integral. I always find non-integral simple modular fusion
But
category.
when you said integral, you mean that the
Integral
dimension?
Frobenius parent dimension of the
Oh, integral per Frobenius parent dimension. Yeah, you're right. Except in very kind of very simple ways that it's pointed. All of them are non. Yes, but for at least these examples, SON level 2. Oh, it's very long, the presentation. Those examples, they are not, I mean, they don't have integral dimension, but at least the dimension of the objects to the square is an integer. So the whole dimension of the category is an integer number.
weakly integral.
But again, this is not exactly, yeah. It's weakly integral. Yes, that's the word. Yeah, it's weakly integral, but it's not integral. You're right. Mhm.
Do you know a reason why nothing is integral in this in this family of fusion category?
Ah. No, I mean, I know the computations, but really like a deep fact, I don't know. Or a reason, let's say that why they are not.
French.
The only thing that I know that is kind of very interesting, and it's related with work that I have been done for some years with Eric Rowell, is that if the, I mean, also to be weakly integral for Verlinde category is very weird. I mean, there are very few examples of Verlinde category that had integral dimension. And the other interesting part is that those that have integral dimension, the braided representation associated has finite image. So it seems to be, again, some kind of deep, and at least for us, for Eric and me, let's say, and not clear. I mean, we know because we have been working on this for a long time, and to apply. In fact, Zesting appeared as a way to prove that, I mean, we had this category. Oh, sorry, this new category, and we didn't know if the new one has a finite image of for every braided representation. And braided testing appears as a technique in order to prove that something that Eric called F property that happens. But again, the only thing that I know, and it's again kind of deep, but I don't know exactly the reason why it's happening, is that integral, it's very weird. A weakly integral is very weird. And this is related with several interesting facts, like that the image of the braid, it's finite, but also with the fact that the not invariant associated with this kind of category can be computed effectively. Something that in general, I mean, to compute things like the Jones polynomial, even with the specific values that corresponds to families of Verlinde categories, very hard. I mean, it's Sharpie complete problem.
Okay. And I have a final question, if you don't have. So sorry for being redundant, but I always ask the same question. Do you believe in the existence of non-trivial, simple, integral, modular fusion category? This is related to the problem of a weakly group theoretical existence of integral fusion category, which are not weakly group theoretical, but what are your feeling about this kind of problem? And in particular, do you believe in the existence of a non-trivial, simple, integral, modular fusion category?
Non-trivial, simple, integral.
Modular fusion category. There is
Oh,
nothing,
I see. No.
there is no one is known up to now.
Yes.
I am looking for, I would like to find one, but as I said, this is related to the weakly group theoretical problem, existence of.
Yes.
What are your feeling about this problem, and in particular in the modular case? Do you believe it is true, it's false, or do you don't believe anything?
to be honest, I mean, something that I believe has a lot of possibilities to be true. It's the that every integer will be weakly group theoretical. I think this is a very deep statement. Yeah, I think this is a but to be honest, I have no idea at all how to attack the problem. I mean, at this moment, it seems that it's really hard.
If you have no clue, why do you believe this is true? This is what I am interested in, because most of
No. I don't have any. No. To be honest, I don't have a reason that I can. I mean, this is not a good reason, but we have been. I mean, a lot of people in the community have tried for many years to construct examples in many directions. At this moment, well, this is not an answer, of course. So really, I don't know. I have no a concrete answer to the question.
Thank you. So, is there any question, for example, in the online? If someone has a question online, please unmute yourself, or you can write the question on the chat. We can wait a few minutes, otherwise we will stop here. Yeah. Can you send me your slides?
Sure. I will do tomorrow.
Yeah, thank you. Okay, so if there is no question,
well, it was a pleasure.
Yeah. No other question. Okay, so thank you again.
My pleasure.
And
okay.
I hope to see you in Beijing if you are interested.
I would love to be. It's kind of far, but yeah, it will be an experience. I have never been in China.
It's a very big conference every year at our institute called. It's new. I don't know if you have heard about that. It's called ICBS, and it's every year. It's very nice.
Yeah.
Okay, so
I would like to pay. I will pay attention to that.
I will send you the link. Thank you again.
Thank you.
Bye bye.
Okay, well, my pleasure. Bye.
Bye.